is stretched and fastened in 2 points which are at L distance apart. That means a string is stretched and its endpoints are fixed. The fixed endpoints are at L distance apart from each other. The string moves satisfying the one-dimensional wave equation, and displacement of the string is in the form of curve given by y equals a times sine pi x by L, and the string is released at time t equals 0 from rest position. We have to show that displacement of any point at a distance x from one end of string at time t is given by displacement function y of xt equals a sin pi x by L cos pi ct by L, where x range from 0 to L. The same question can also be written as a tightly stretched string with fixed endpoints x equals 0 and x equals L is initially displaced in sinusoidal arc, which is at height a and released from rest. Find the displacement function y of xt. We have this parameter a which determines the height of the sinusoidal arc. Let us look at the solution. Since moment of the string satisfies one-dimensional wave equation given by dou square y by dou t square equals c square times dou square y by dou x square, which we call as equation 1, and we have the boundary conditions given by y of 0t equals y of lt equals 0 for all t values greater than or equal to 0, and initial conditions given by y of x0 equals f of x, and in our question f of x is given as a times sine pi x by L, where f of x is the initial shape or initial deflection of the string, and the velocity is given by dou y by dou t at t equals 0 equals g of x. Here, since string is released from rest, we have g of x equals 0 because there is no initial velocity when released from rest position. We have the most general solution for equation 1 is obtained as y of xt equals summation n range from 1 to infinity a n sin pi n x by L cos pi n ct by L plus bn sin pi n x by L sin pi n ct by L, which follows from Fourier series solution of one-dimensional wave equation, and we have an and bn are Fourier coefficients. An is given by the formula 2 by L times integral 0 to L f of x sin pi n x by L dx, and bn is given by the formula bn equals 2 by pi nc multiplied to integral 0 to L g of x sin pi n x by L into dx. Since we have g of x equals 0, we will have Fourier coefficient bn equals 0. It is enough to evaluate values of an. When n equals 1, we have a1 equals 2a by L into integral of sin square pi x by L into dx. We have just given n equals 1 and we obtain the integrand as sin square pi x by L into dx. We have the standard formula cos 2 theta equals 1 minus 2 sin square theta, from where we have 2 times sin square theta equals 1 minus cos 2 theta, and thus we have the relation sin square theta equals 1 by 2 times 1 minus cos 2 theta. We will have theta equals pi x by L, and thus we have sin square pi x by L rewritten as 1 by 2 times 1 minus cos 2 pi x by L. 1 by 2 can be taken outside the process of integration. Integral of 1 with respect to x is x, and integral of cos 2 pi x by L with respect to x is obtained as sin 2 pi x by L upon pi by L. When you give upper and lower limit to this term, it becomes L minus 0. When you give upper and lower limit to second term, it becomes 0 in both cases because sin 2 pi and sin 0 are both 0. When you give upper limit, this becomes sin 2 pi L by L, which becomes sin 2 pi in the numerator, which becomes 0. When you give x equals 0, again you get sin 2 times 0, which is sin 0, which is again 0. You have a non-zero answer when you give x equals L here, and we have a1 equals small a. When you evaluate a2, giving n equals 2, you get a2 equals 2 by L times integral 0 to L a sin pi x by L multiplied to sin 2 pi x by L into dx. Since we have the formula 2 sin a sin b equals cos of a plus b plus cos of a minus b, we have this integrand rewritten as cos of pi x plus 2 pi x by L plus cos of pi x minus 2 pi x by L into dx. A is taken outside process of integration. Integrating this term, you get Sine 3 pi x by L upon 3 pi by L. Integrating this term you get sine negative pi x by L upon negative pi by L. Or here you can simplify it as cos of negative pi x by L, which can also be written as cos pi x by L itself, because cos negative theta equals cos theta. Giving upper and lower limits, we obtain these two terms become 0, and thus we have a2 equals 0. Similarly, we have a3 equals